Hello everyone, so we are going to speak about Arduino Create. That's a new platform, an ecosystem of many different applications. It's mainly based on an entire new stack, and we build a complete new migration from EC2 standards, so AWS services, to something that's more not just modern, but also vendor independent. So we move everything to Kubernetes. And we will see if we want later on eventually change provider, or just we can deploy it again in some container inside containers, you know, like Inception for containers, directly on-premise or on some small gateways. So that's the story about us and also about our overall new architecture. So I'm it's written CTO, but it's not CTO, it's CIO.
You could also change the photo because
yeah,
you want to be probably.
Yeah, it's something like that.
Yeah.
And so, yeah, I'm the CIO of Arduino. We are also hiring as well, so just send us some CV if you like. And we have Matteo here.
I'm a backend developer and developer.
And let's just dive in the issue and how we solve the issue that we have. So the problem from a pure technical point of view is that we really had a lot of multiple applications. More or less, we had 18 legacy applications, and then it sorted out to be something like probably few dozens and maybe soon few hundreds microservices. So some of them are with this structure, so api.arduino.cc, then the name of the application, like Arduino Create, then the version, which is not strictly, you know, REST APIs if you have the version in the URL, but it's nice to have, and I would say kind of a standard, even if not pure REST, and then the name of the endpoint. The same happens with another thing, which is the builder. That's something that compiles online and gives you an artifact. At the same time, we also have an API development endpoint, which is still publicly available, even for development, because we have a huge community and we want to involve them even in our development stage. So users know that could break, but can help us in finding issues before they appear in production eventually. So there are many different processes on how we expose those APIs, and this is like, for us it's already an old architecture, even probably for many companies looks like super modern. So it's very standard, like you have a client, you have an endpoint, DNS endpoint, API Arduino CC, then you have a load balancer, a set of instances with autoscaling, and then Nginx that proxy every different application to different endpoints. So pretty standard, would say, in the last few years. It's stable, more or less works. It doesn't scale super fast. The nice thing is that it's scalable enough and with high availability, but I said it's not super fast and it's a bit too complex if you want to go out of AWS. Plus, the auto-scaling is not extremely easy. I'm going to explain why. So every instance needs a whole copy of the entire application, which could be nice if you really have microservices for everything. But some of the applications, you know, are very hard to be modular, or in any case, you take some time to do that. So it's super nice if you start a new application from scratch, but if you have a big legacy application used by 100,000 users per day, it's not that easy that you just create a new module and do that. The other thing is also to separate the traffic between different load balancer given a specific endpoint, like /create goes to a set of load balancer and /builder goes to another one, or you just want to have multiple endpoints using the same DNS resolver. The other thing is also to have logs. So either you have a log aggregator or managing the logs on every, I don't know, Nginx machine or any application. It starts to be very messy because if something fails and your server has been completely destroyed by the autoscaling group, then it's very hard to figure out what has been done that completely broke your application. So it's still, again, doable, but there is a lot of, wouldn't say completely manual process, but still manual mindset. The other thing is that you basically need a complete whole copy of the production environment and the development environment, also from an infrastructure point of view. So despite the fact that you only have less instances, every other cost is basically duplicated, and usually the CFOs is not too happy about that. The other thing is that if you want to auto-publish new applications, they cannot really auto-publish, but you have to define them in Nginx, roll an update. Sometimes you need to even reload Nginx, which is not really something super nice for the users because they could lose some connections, especially if you do WebSocket. If you do WebSocket over an Elastic Load Balancer, then good luck. So, you know, it's not really simple. So we decided to, this is like the old, again, the super old stack, which was working. So we had GitHub deployment, automatic deployment based on drone. So that's the drone logo. We uploaded the binary on S3, and then we ran with the CI system after all the tests were passed. We ran a simple SSH login on our source stack server that basically triggered the deploy. It was working. It was working, yeah. And it was also scaling in this way. How? We used Datadog for monitoring. So we were able to send an alert every time we had a new deploy. How that worked? Basically, there was a Python script somewhere on a monitoring server, let's say, that was checking the CPU load average of the whole, of every server of the autoscaling group, and if the mean of the load of every server was half than 80% for more than 15 minutes, we just spawn a new server. Spawning a new server is nice because also for our own choice, we decided not to have an image of this server, but we always start with a plain Ubuntu stock image and then reinstall everything all the time because we want to be sure that the deployment is 100% reproducible. So it was working like this. You have events in the Datadog. It basically sends you a webhook to an endpoint. In the monitoring server, then we had SoulStack Cloud that was able to spawn another server. Again, it was working for a couple million users per month as a main usage until it basically broke completely. And no one was really able to figure out what was going on. Why? Because, as I said, logs were super confusing. You know, once you are working with a lot of different developers, we also had a company, basically a rebuild of the whole company some months ago. So some developers left, some others were hired, and didn't know the whole architecture. There was no documentation, so you know you have trouble in production, and it's not nice. So we fixed that, I think, in a couple of hours, more or less, but still was not super scalable. So it was up and running, but it was not scaling anymore very well.
We had to scale it manually.
Exactly. So our scaling procedure was, if something, look at Datadog all the time, if something goes too wild, just spawn a new server. It was kind of, okay, it is manual scaling, that's it. Exactly. So that was partially good. Obviously, it was good for development, was good for staging, but for production and for massively scaling was not good anymore. Especially because the growth rate of Arduino Create is more or less 16% every 30 months, based on something like it started when it was 100,000 users every day. So at 16% of growth every month, you know, it's like an exponential number of users. So we are almost at 500,000 users now, every single day, which is like, so this was kind of our new idea, which is like probably looks 90s for some newspaper companies. So you have like DNS, then you have a CDN, and then you have static HTML, which is like so new that really looks like in the 90s. Probably the first web server was exactly like this, no? You know, just a single desktop connected to the network of the university. There were no CDN, but everything else is like static pages always work and infinitely scale. It's super efficient, it costs nothing, and it works. Zero maintenance is basically all that. So again, here there are a couple of components that are really vendor locked in. Like S3 is an object storage. So you know files. Okay, this is not really a file. Is that a database? Kind of. What kind of interface has? Maybe a driver. Yes, the driver is named HTTP. Oh, what a kind of database is that? So that's exactly what the bucket does, S3 does. Then you have CloudFront, which is a CDN. Okay, it's nice to have a CDN. The fact is that having a global CDN with a lot of different endpoints like /devices, /static, whatever you like, means that you need a lot of different rules to handle every single endpoint, just because we want to be nice to the user and only have api.arduino.cc for thousands of different applications. And to do a CDN the proper way that handles the routing in the right way as we want it is not easy for anyone, and not even for Amazon. So Amazon is not really, it doesn't have a nice way to do that, just because it's not designed to do that. And also because it's an art problem. The other thing is Amazon Rules 53. There is someone here that knows DNS very well. You know, DNS is that kind of thing that when you look at the specification, it looks like, oh, so easy. And then you end up like, but if I really need to implement that at a global scale, it's going to be impossible, just impossible. And Amazon did a pretty good job and has nice APIs. But that means that you're using Amazon, then Amazon, and then Amazon. And if you want to migrate to, I don't know, Azure or Google, or have your own open stack or OpenShift or whatever you want to use, you basically cannot. So yeah, that was the whole point, to have create.arduino.cc/devices. So in the front, this is the front end, the back end I've shown you before. So that was, it's task to think, okay, what we can do again, otherwise we have to fire people, no? So we have to keep them engaged in something, like giving them tasks. So we say, okay, rebuild that all the time. It's like having, I don't know, builders building your house, and every a couple of months you say, okay, let's destroy the whole house, and we do that from scratch and make it nicer. It's that kind of process. So we continuously rebuild everything, so we don't get fired by the management. And so we decided to use something that was new, that was cool, modern, even if we know there are a lot of limits. we try to keep it extremely simple. Really extremely simple. What does it mean? That it works on your PC the same way that it works on the cloud for million users. So that's the story, and now Matteo is gonna tell us how it works.
Okay, so we decided to use Kubernetes and traefik. Kubernetes is an orchestrator of containers. It means that you build the containers and it decided where to put the containers in your list of nodes, and you don't have to worry that much about where the containers are. It allows you to deploy multiple versions of the application, to do blue-green deployments, and also it has a very nice command-line interface. I really like it. And traefik is a reverse proxy, kind of like Nginx, but it does a lot of nice features like auto reload of the configuration. And also it interfaces directly with the Kubernetes API, which is what we really need. So this is how the cluster looks now. The client requests the address to the DNS, which is still root 53, but it can be changed anytime. It goes to a load balancer, which will split the traffic between all the traefik containers, and they will decide where to send the traffic based on the host and the path and every other rule that you say. For example, the traffic on api2.arduino.cc/devices will go to the devices service, which is a collection of containers. Otherwise, the traffic on web.arduino.cc goes to the web service. It's API2 because we had to we moved every container once at a time from the old infrastructure to the new, and right now we are at the final stages. We still have two microservices to migrate to Kubernetes. So, what are the advantages? The pods, which are the collections of containers, can scale separately. So if you have an application that requires a lot of, that serves a lot of traffic, it can have a lot of resources, while other that don't do very much are scaled down. We have one load balancer, which is great mainly because of management, because we had like a 30 load balancer at one point, and it was crazy. We had to ask Amazon, can we have more load balancer? And it's also easier to aggregate logs because Kubernetes comes with a lot of kind of built-in log services. Right now we use Fluentd, which uploads data to Sumo Logic, and it took like half an hour to set it up, so it was great. And it's cheap to run staging or canary instances. For example, if we need a staging instance to test a branch for like 3 hours, but in the meantime we have to test another branch, we don't have to create another stack of server, but we can just run a container. And it's also easy to go multi-region. At the moment we are not doing it, but it's basically you have to just replicate the whole cluster on another region and use a regional load balancer to split traffic, and it's pretty easy to do. So here is the code. Right. This is the deployment. If you have used Kubernetes, you know what it is. It's basically the description of the application. The important thing is here is the image, which is our internal Docker repository, which uses, it says that this is the email API application with the prod level. And image pool policy always, because this way we can overwrite the prod label, reload the services, and it will pull the latest version all the times. It's also pretty nice because our images are very small, like 10 megabytes. A service is a collection of pods or containers that are exposed to other containers on the cluster. Here at the port 80, Kubernetes will give them an IP address, and so the other containers can talk directly to them without going out to the internet. Yes. The Ingress is where the magic happens. A Ingress is basically a point where the traffic can enter and be routed. You can see there that we define the host and the path and where will it goes. This says that traffic at api2.arduino.cc with a path of email has to be redirected to email API prod. Traefik is marked, and thanks to that annotation, Ingress class traefik, it understands what to do. So we just by configuring Kubernetes, we can also configure traefik, which is pretty great because in sometimes we could switch traefik for something else, and if they interpret correctly the Ingress, it will still work. This is the autoscaling group. There are two kinds of autoscaling in Kubernetes. One is the horizontal pod autoscaler, which means that it counts multiple instances of the pods. And the other is the vertical autoscaler, which creates new servers. The vertical autoscalers, it depends on where you have the cluster installed. We have it on AWS, so we are using a cluster that already has it, so I have no idea how it works, but it does. This says that we have a minimum of 2 replicas, 2 because if one goes down, there's another. And a maximum of 5 because this one never went up to 3. It was always stuck at 2, so it doesn't need much. And the target CPU utilization percentage is the amount of CPU that the container is using, must use before Kubernetes decide to add another. The traefik service account, it's needed by traefik so that it can read the Kubernetes configuration. It's pretty easy. And the traefik deployment is how we are deploying traefik. It's a container just like the other, it's a deployment. And we are using the version 1.4. I don't know if there is a new version, but this one is working nice. And we say that it has to spawn with the target Kubernetes. So it will understand that it has to read the configuration from Kubernetes. There's also a way to give it a configuration via classic text file, but I didn't include it because we are not using it. The service is the same thing as the other service, but this one has the tag not port, which means that it's exposed to the internet. External traffic policy, I don't remember what it does, but we had to put it to preserve the IP address of the incoming request. This one is exposing the port 80 for HTTP and the port 443 for HTTPS. But the HTTPS is actually handled by the load balancer, and in the cluster all the pods communicate with HTTP, which is not a problem because they are not exposed, but there are in another cluster that we are working on, we are making them communicate all with SSL, which is a big can of worm. We are working on it, maybe next time we'll talk about it. So, this is the autoscaling of the traefik, which is basically the same. We have more replicas for traefik because it basically handles every request that comes. But at the moment it's behaving pretty well. It's it's very fast and it's not giving us much trouble. Okay, so before I said that our containers are very small, like 10 megabytes. That's because we are building them from the scratch Docker image, which is the littlest and barest image that you can think of. We add the SSL certificates so that they can understand what SSL means. And we add the binary and some other folders that the application needs. And this one creates basically a single binary that is wrapped into a container. And they are very small and we like it very much because they are pretty instantly deployed. Now we can scale up from one server from 3 server to 4 in like 3 to 4 minutes, while before it was like 20 to 30 minutes, which kind of defeated the point because by the time the server was up, the request peak was down. So those poor servers never had to do anything. Anyway, we finished. We are Arduino, you said before, we are hiring, so write us at just.arduino.cc if you want to work on that with us. That's it.